Good Wednesday day, I guess I should say, everyone. Welcome to the Chem Help ASAP live stream. We are starting just a smidge late today, but I hope that doesn't mess anybody up. Okay, so tonight we are going to be working some equilibrium problems, which means we are going to be working through some math. We're going to use a quadratic equation a little bit. Yes, we're just going to be working through a lot of different mathematical steps. We're not going to do too many problems because these tend to be rather long. And one thing I thought about, let me know in the comments, is I don't really go over Le Chatelier's principle because we're just working through the math, but that is something to consider for a future live stream. Okay, with that being said, let's go ahead and start our first problem. All right. So the first couple of problems that we're going to do here is we're just going to predict which way the equilibrium is going to shift, if it's going to shift left or right. So this is, well, not really Le Chatelier because we're actually going to do it mathematically, but it ties into that. Okay, so you can see over here on the far right, I have these different relationships between Q and K. I suppose I should lay a little foundation here. So K is your equilibrium constant. Q is basically a test that you run to see which way the equilibrium is going to shift. So if Q equals K, when you calculate Q, that means the system is already at equilibrium. If Q is greater than K, that means the system is going to shift to the left or towards the reactants. And if Q, I said less than, if Q is greater than K, it's going to shift left. And if Q is less than K, it's going to shift right, or it's going to shift to the products. So the first couple of calculations that I want to do is we are given K, we are going to calculate Q, and we're going to determine first if the equilibrium is going to shift and also which way it is going to shift. So I hope that is clear as mud, I guess I would say. All right, so let's get my pen up here and we are going to just start with problem A here. So you can see we've got our chemical reaction. This is our classic formation of ammonia. We are given our value of K, and now we are given initial concentrations, and we want to know which way the equilibrium is going to shift. So we need to calculate Q, and we will compare that with K. So let's go ahead and just for this part A, let's get our expression for Q. Now when you write your expression for Q, it's exactly the same as for K, except you're putting in initial concentrations. So it's still products over reactants. All right, so Q for my reaction here is going to be my initial concentration of ammonia squared. Again, this squared comes from the stoichiometric coefficient, and that is over my initial concentration of hydrogen, and that is going to be cubed. Again, I'm looking at my stoichiometric coefficient times the initial concentration of nitrogen, and that's just raised to the first power because, again, the stoichiometric coefficient there is 1. So this is how we're going to calculate Q for both part A and part B. Oh, whoops, there's a typo there. For both part A and part B is we are going to put in our initial concentrations and we are going to calculate what Q is, right? Okay, so, I have done these calculations, but definitely use your calculator to do this. These are not ones that you do in your head. All right, so we have our initial concentrations. So Q, we'll call this maybe QA for part A here. Let's get these concentrations. So ammonia is 1.0 times 10 to the negative third, and that is molarity, and we are going to square this. And we're divided by our initial concentration of hydrogen, which is 2.0 times 10 to the negative third molarity, and that is cubed. And we're going to multiply this, continue that by our concentration of nitrogen, which is 1 times 10 to the negative fifth That is measured in molarity. And this will give us our value for Q, again, for part A. That doesn't mean acid. I'm just using that for part A. So when you put this in your calculator, and I have done this calculation, you get 1.3 times 10 to the 7th liters squared over moles squared. Okay, so now we want to take this value of Q and we want to compare it to K, and we're going to say, are they equal, greater than, or less than? Again, I'm using this table over here in the upper right. So definitely Q does not equal K. What we've got is we've got Q, this is 10 to the 7th, this is actually much larger than K. So we've got a Q is greater than K situation, which means we are going to shift to the left, or we're going to shift back to the reactant. So we're shifting in this particular case to the hydrogen and nitrogen gas side of the equation. All right, so it's pretty simple. We're just plugging in initial concentrations, and then we are calculating Q. Let's go ahead and do this for part B. So again, we're going to calculate Q the same way, except this is going to be part B. Again, I am using this expression right here, but we have new initial concentrations. Okay, so our concentration for ammonia is 2 times 10 to the negative 4th. And that's in molarity. Oh, sorry, that should be squared. Don't want to forget that. That is kind of a classic thing to do when you do equilibrium problems. It's very easy to drop a squared or a cubed or something like that. So let's go ahead and go on to hydrogen gas, which is 3.54 times 10 to the negative 1th, and that is going to be cubed. And then we're going to plug in for our nitrogen gas, which is 1.5 times 10 to the negative 5th. Oh, I forgot my units here. Sorry, that is molarity. I'm going to squeeze that in right there. Okay, that is nitrogen. So if you put all that in your calculator, and I did this calculation, we get 6.01 times 10 to the negative 2nd, and that is liters squared over mole squared. And you can see that our Q is equal to our K. So QB is equal to K. And it's okay that this is 6.01 and this is just 6. If we were to round this to the correct number of sig figs, it would round to 6. So this means this system is at equilibrium. Now, one thing that I do want to do, and make sure we don't have any questions, is I do want to run through these units really quickly because I've just been putting them down, but it's kind of nice to see how the units work out. All right, so all of these are concentrations in molarity, and you can see K has the units of liter squared over mole squared. Well, where does that come from? How does that work? Okay, so if we go back to our expression for Q, and I'm not going to put any numbers in, I am simply going to put units in. That means we're going to have molarity squared in the numerator, and this is going to be over, remember this is cubed, so that's still measured in molarity, cubed, and nitrogen is also measured in molarity. Okay, so this simplifies to molarity squared over molarity to the 4th, and again, remembering your rules for exponents, this is the same as 1 over molarity squared. And if you remember molarity, okay, so I'm going to switch down here. 1 over molarity squared, remember molarity is moles per liter, and this is squared. So if we have 1 over, it means we take the reciprocal, so that is the same thing as liters over mole squared, and now you can see where we get this liters squared over moles squared. So your K will have units and they will actually work out, and what's kind of interesting is Your values of K are unique to your reaction, and very often the units are also unique to the reaction or the type of reaction. So if we had another reaction that was a 3:1:2 reaction, then our units would also be the same. But I did want to show before we left this problem that the units actually do work out. Okay, let's make sure there are no questions. Nope, no questions. Let's go on to our next problem. Okay, so this is where we are really going to get into it. So we want to calculate the equilibrium concentrations, and we are given initial amounts here. We are also given a K as well. All right, so there is our balanced chemical equation. Now, for concentration, we want to use molarity, and that means we need moles per liter, and we've got grams here. So actually the very first thing I'm going to do is I am going to convert these grams to moles and then convert it into molarity. So this is just another example of how converting between grams and moles is something that you're going to use continuously while you're doing chemistry. So it's not one of those skills that you kind of learn and then you put away. You are always going to be using it. All right, so if we have 1 gram of water, we need its molar mass to convert it into moles. And its molar mass is 18.015 grams of water over 1 mole of water. And that gives us 0.056 moles of water. Now, the nice thing about this problem is you can see we are added to a 1 liter vessel, which means to convert to molarity, we're dividing by 1, which means that its molarity is the same as its number of moles. That is now molarity. Okay, that's great. That makes calculations at least a little bit easier. Okay, let's do the same thing with our 2 grams of Cl2O. Again, we just use the molar mass. That is 86.905 grams Cl2O over 1 mole. Okay, so this one is 0.023. That is moles of Cl2O, which again, because everything's put into a 1 liter vessel, this also gives us our molarity of Cl2O. Okay, and we don't have any HOCl. So that is just 0. We don't have to do any conversions from grams to mole. Okay, so again, just like we did before, we want to know which way the equilibrium shifts. Now, if you are, this is why I thought maybe I ought to throw Le Chatelier in here. If you're familiar with Le Chatelier, if you have nothing on one or other side of the equation, the equilibrium is going to shift to produce. Either if you have 0 product, it's going to shift to product, or 0 reactant, it's going to shift to reactant. So I already know, just based on Le Chatelier, that we ought to be shifting towards product here, but we can still calculate Q and use our rules here and determine which way it's going to shift. So we can use either or, and they should agree, they should match up. Okay, so let's calculate Q. Okay, so this, just based on our reaction, is our concentration of our acid here over water and Cl2O. Okay, that's great. So we have our initial concentrations. Now remember, this is 0, okay, squared, over 0.056 molarity over 0.023. Again, that's molarity. And so you can see that Q equals 0, right? Because 0 divided by anything is 0. But I know that kind of throws people a little bit when Q equals 0, but Q equals 0 actually doesn't mean anything on its own. We still have to compare it to K. And in this case, we have a K of 0.9. So our Q is less than K. So we are going to shift to the right, which totally makes sense because we need to make product. We have no product, that is 0. So again, Q equals 0 doesn't mean anything specifically. It just means compared to K that this reaction is going to shift to products, or it's going to shift to the right. All right, so now we know which way it's going to shift. We need to set up our equilibrium calculation. And what I think I am going to do here is I'm going to shift to another, I'm going to get another page because we're going to need some more space. Okay, all right, so I'm going to get our reaction written up here at the top of the page again. We've got water plus Cl2O, and that is in equilibrium with HOCl. All right. Now that we know that the equilibrium is going to shift to the right, we can set up our equilibrium table. A lot of people call these ICE tables, where you have your initial amount, your change, and then what your equilibrium concentrations are. Okay, so we already calculated what our initial concentrations are, so let's actually put those in. Again, these are, I'm just pulling these concentrations right here. Okay, so I'm going to write each concentration underneath the molecule that it represents. So our initial concentration of water was 0.056. Our initial concentration of Cl2O was 0.023. Let me make that decimal a little bit bigger, and we have no HOCl. All right, so if we are going to shift to the right, that means we're going to end up with less water, less Cl2. So these are going to be negative signs. So I am going to have this as negative X and negative X, and it means shifting right, we are going to be adding to our products. So this is a positive, oh, sorry, I didn't balance this equation. This is a positive 2x. So this is why it's so important to know which way the equilibrium is going to shift, because it tells you where your signs for your x's are. So shifting to the right means that this 2x is positive and these are negative. But obviously if you were shifting to the left, to the opposite way, then you would have to flip-flop your signs. Okay, now we can get our equilibrium concentrations, and we're simply just adding down this column. So this is still more, I feel like, the conceptual part, and we are getting ready to go into the math. Okay, because of course we can't actually calculate these concentrations without knowing what X is. So our really heavy mathematical part of this problem is calculating what X is. And to do that, we are going to use the equilibrium expression and our value for K. So K is products, make sure that's squared, over reactants. So here's our water and our Cl2O. And we actually know our value for K. Again, let me just pop back here. We are given this value right here. Okay. And actually, I just realized that there is a typo here. This should be 0.090. And I left out that 0. I just transcribed the problem wrong. Okay. But that's all right. We can still work through everything. So now what I'm going to do is I'm going to take my equilibrium concentrations here, and I'm going to plug into K, and I am going to solve for X. All right, so here we go. My concentration of HOCl is 2X. Don't forget to square it. My concentration for water, this is just going to get rather large. And concentration of Cl2O minus X, and this still equals my 0.090. Okay. So you can see I have one equation and one unknown, but this is not necessarily a trivial thing to solve because we're going to end up using the quadratic. You can see this is already going to be an x squared. So you need to be prepared to use the quadratic equation. Now, the thing that I recommend, I'm going to go through the algebra of this, but the thing I recommend is using your calculator to do the quadratic equation. So many calculators come with quadratic equation already programmed in. If not, you can program it in yourself. But yes, again, if you have a graphing calculator, if you have just about any of the TIs that are programmable, you can get the quadratic equation in. But let's work through a little bit of this algebra first. Let's get the quadratic in the proper form so that we can use the quadratic equation. Okay, so I'm going to FOIL the denominator, and of course we're going to simplify the numerator. Okay, so this is going to be a 4x squared, and my denominator is going to look really nasty here. Don't panic, it is supposed to look terrible. These are very different from, say, the quadratics that you would solve in your math class where you have usually nice whole numbers or maybe one decimal place. Okay, and this still equals my 0.090. So what I'm going to do is I'm going to take this quantity and I'm going to multiply it to bring it over to the right-hand side, although I think I'll just rewrite it, okay, like this, because I really want to have, oops, forgot that 0. Okay, so here is my denominator that I moved over, plus x squared, and now that equals 4x squared. So you see how I took this quantity here, multiplied it by both sides, so it came up into the numerator, and I'm multiplying it by 0.09. Okay, so we're going to get, I'm coming up here, we're going to get, again, just really ugly looking numbers here, but bear with me, they will work out. Again, we're trying to get this quadratic in a form that we can use a quadratic equation for. 711x 9x squared. Okay, and this still equals 4x squared. So all I need to do is combine my like terms here, and this will give me the quadratic in a form that I can use a quadratic equation. This is kind of the algebra that you have to slog through to get your answer. 9(1)x squared, and now this equals 0. Okay, so here is your value for A, here is your value for B, here is your value for C. Again, use your calculator to do this. You can do it by hand, but it gets really messy with these messy decimals. Okay, so when you use the quadratic formula, you'll get two values of x, of course, because it is a quadratic. So we will get a value for x that is negative 0.0064, and we get a second value for x that is 0.0046. So then the question becomes, which value of x do you use? Well, this is actually a really easy case. You can't have a negative value for x. So I'm just going to cross through that one, which means automatically this second value for x is your correct value for x for this equilibrium problem. Now that we know what x is, then we can go back and calculate our equilibrium concentrations. All right, so our equilibrium concentration for water, again, this is equilibrium, is going to be our 0.056 minus x, which we know the value of. So I am actually going to plug that value in. And that gives us our equilibrium concentration, which is 0.0514. And we just do the same thing for all of our species. So again, our Cl2O, our equilibrium concentration, again, I'm using this formula right here, 0.23, again, just minus x, and x is right here. It's very easy at this point when you've kind of slogged through the quadratic equation to stop at x and go, okay, I solve for X, I'm done with the problem. But really, the problem wants your equilibrium concentrations. So hang on, keep going, and get those equilibrium concentrations. Okay, so I did this calculation, and this is 0.0184. Again, these are all molarity. I should put my units in. And then let's do the same thing for our product. This is simply 2 times X. So 2 times our value for X. And that gives us 0.0092 again, and that is molarity. Okay, so this is or I should say, these are the equilibrium concentrations when we have initially 1 gram of hydrogen and 2 grams of Cl2O put into a 1 liter vessel. So, that was a lot of work for a seemingly simple problem, right? Okay, how are we doing on time? All right, we've got time for our one more. And again, these do take a little bit of slogging, but it's very satisfying when you get to the end, I find. All right, so our final problem here. Again, we want to calculate, in this case, equilibrium pressures of our reaction right here. And we know initially we've got 2.5 atmospheres of both of our reactants added to the vessel. Okay, so I'm going to skip calculating Q because this is the same example we had before where we have no product. We know that the equilibrium is going to shift to the right, is going to shift to make some of those products. I mean, the question is how much. But we have another problem here that we need to deal with. So we are given a K, which is definitely coming from a concentration, and we need to calculate a Kp because we have pressures here that we are dealing with, and we're trying to calculate equilibrium pressures. So K, or sometimes called Kc, is not the same thing as Kp, and we first have to convert between. But it's not that difficult. So let me get the equation up for doing that conversion. So if we are going to calculate Kp, we are going to take K and we are going to multiply it by RT raised to the delta N. So let me break this down just a little bit. Kp is your equilibrium constant with pressures. When we just write K, or sometimes you'll see it written as Kc, that is your equilibrium expression with concentration. So again, this is just a conversion to go from concentrations to pressure, and the way we do that is we use R, which is our universal gas constant, times our temperature, which thankfully our problem gave us, and our delta N. This is our change in our number of moles. And delta N is simply your products minus your reactants. So you've probably seen that if you've ever calculated delta H or delta S or delta G. It's always products minus reactants, but in this case, it's the number of moles. And what you're looking at specifically is your stoichiometric coefficient. So for this reaction, what is the stoichiometric coefficient in front of our products? Well, it is 1. And what is the stoichiometric coefficient between our reactants? We have a 1 and a 1. So that is a 1 plus 1. So in essence, we have a 1 minus 2. So our delta N in this case is a negative 1. So I want to make sure you know where that number comes from. And you're just looking at the stoichiometric coefficients. In this case, products was easy because there's only one product. But if you had 2 products, you would add those stoichiometric coefficients together first, and then you would subtract it from the sum of the reactants. And I think we are ready to actually calculate our Kp now. All right, so we already have our K. That's 4.5 times 10 to the 9th. That is liter mole. We are going to multiply by R. Now you want to be careful of your units here. So I'm going to choose a value for R that has liters and atmospheres, because you can see I want to go to atmosphere, and it's also going to have mole. Now that is going to give me a mole K, which means for my temperature, I am going to have to convert to Kelvin. So if you have done gas laws before you did equilibrium, which you probably did, you're probably very used to converting Celsius to Kelvin when you're dealing with gases. And this is the same thing. We're going to have to convert to Kelvin for this. And actually, I can do this up here. This is 373 Kelvin. Okay. So my value for R, again, if I'm using liter atmosphere, it's going to be the one that you probably used the most when you did gas laws. Okay, so this is liter atmosphere over mole K, and that is 373 K. And actually, I think I'm going to put brackets just so it's clear. This is to my delta N, which I calculated up here, to the -1. So you know that first we're going to multiply in the brackets, and then we are going to take the inverse. So again, this is where knowing your order of operations is also really important when you're doing all of this math. Okay, so let's just slog through this a little bit. This is 4.5. That decimal got a little janky there. Okay, 10 to the 9th liters over moles. And then this is 30.6. This is now liter atmosphere over mole. Again, my Kelvin canceled out there. This is to the -1, which means it's just divided. So what we're doing here is we're going to take 4.5 times 10 to the 9th liters per mole, and we're going to divide it by our 30.6 liter atmosphere over mole. And this is going to give us our Kp, which is 1.47 times 10 to the 8th. And you'll notice that our liters and our moles cancel. We're just left with atmospheres in the denominator. So this is atmospheres to the -1, or the inverse of atmospheres. You can also write 1 over ATM if you want. It doesn't make a difference. Okay. The point being, we now have Kp, so we can actually do our equilibrium problem. Again, I'm going to skip the calculation of Q because we know it's already going to shift to the right. But just like we did before, I just don't think I can fit this in this space. So I'm going to give myself another page here. All right, so let's write my reaction at the top. So now we're going to set up the ice table. Is in equilibrium. All right, so we know we have 2.5 atmospheres of both of our reactants. Sorry, my decimals are not coming through, and we have nothing over here. So again, this is initial. Change equilibrium. So that means that I'm going to have -x on both sides here and x over here. I'll make that plus x. That is the positive side. So my equilibrium pressures are going to be 2.5 minus x for both of my reactants, and simply x for my products. Okay, so let's write my equilibrium expression for Kp. Is simply the pressure of my product over each of the pressures of my reactant. All right, so let's get some numbers in here. So this is simply x over 2.5 minus x times 2.5 minus x. Okay, so now we get to start slogging through our just all of our algebra. Oh, sorry, we do have our value for Kp. We spent a lot of time calculating that. Times 10 to the 9th, and that is atmospheres to the -1. Okay, so I'm just going to focus on the right-hand side of this equation right now. So this is going to be x. I'm going to FOIL my denominator, and this is going to give me plus x squared. Now I'm going to take this quantity over to the left-hand side and multiply through by 4.5 times 10 to the ninth. Oops, sorry about that. Okay, so once I do that, again, you get really nasty numbers here, but that's okay. Don't panic. It's totally fine. Plus 4.5 times 10 to the ninth. That's x squared, and this equals x. Again, that was my numerator that was left here. And when I bring my x over to the left-hand side, you can see my numbers are so large it actually doesn't do anything. I've got the same thing here. 2.8 times 10 to the 10th, because I am subtracting x from 2.3 times 10 to the negative 10th. This is still 2.3 times 10 to the negative 10th. Subtracting 1 doesn't actually do anything to it. 4.5 times 10 to the ninth, x squared, and this, of course, equals 0. So now I have my quadratic in the proper form. I have my a, my b, and my, oh, this is b. I just dropped my x there. So I can use my program in my calculator to get values for x. And because it's a quadratic, I get two values for x. So I get x is equal to 3.1, and I get x is equal to 2.0. So very often you'll have one value will be negative and one value will be positive, and it's very easy to drop that negative value. But here we've got two positive values, so we need to decide which one is valid and which one is not valid. Well, if I go back and look at my equilibrium concentrations, if I were to plug in 3.1 here, I would get a negative pressure, which we know cannot exist. We cannot have a negative pressure. Pressure only goes down to 0. So that means that my value of 3.1 is not valid, because I cannot have a negative pressure. Or if you're doing concentration, you can't have a negative concentration. So that means my value of x equals 2 is my correct value to calculate the equilibrium pressures here. Okay, so my equilibrium pressure for carbon monoxide, again, I'm just using this expression, is 2.5 minus x, which I have calculated. And that gives me an equilibrium pressure of 0.5 atmospheres. And it's going to be the same thing for chlorine gas, is 2.5 minus my value of x, still 0.5 atmospheres. And then my equilibrium pressure of COCl2 is simply x, which is 2.0 atmospheres. So this is one where actually the very last calculation ends up being nice and easy, which is fantastic. Okay, so well done. We slogged through quite a bit of calculations there. And you can see we're just about at the end of our time. So these do take a good bit of time. So when you're presented with your equilibrium problems and you're trying to calculate your equilibrium concentrations, just make sure you have plenty of time and you don't have any external pressures, and just work through it step by step, taking your time. And I promise you will get to the end of these. So anyway, thank you so much for watching this live stream. If you have any requests for future live stream, you can email me, or you can leave a comment on YouTube. You can leave a comment on this live stream or any of our videos. You can also message me on Facebook or leave a comment on our Facebook page, Chem Help ASAP, and that is completely fine. Okay, well, I hope you guys have a great rest of your Wednesday, and I will see you next week. Bye.